So today, Piotr Sulkowski from the University of Warsaw will give his second talk on symmetric quivers and theories of various dimensions, 2, 3, 4, and topological string theory. So Piotr, please.
Okay, thank you again for a chance to speak. So what you see is the slide I already showed tomorrow, which is supposed to summarize connections of this symmetric quivers to different physical theories that arise in various contexts, and usually these physical theories have some connection with various areas of mathematics. Maybe I should stress that I stress this role of symmetric quivers, but for us, I mean physicists, they encode some structure of some class of three-dimensional theories. So I don't go that much into those explanations, but even if for you it may not be sometimes clear why we want to discuss some problems, let me just try to assert that there is some physical motivation related to those like 3D n equal to theories or other classes of theories. And what I presented yesterday was like the bottom part of this picture relation of this 3D theories that correspond to symmetric quivers to essentially some versions of Chern-Simons theory, in particular, which encode not invariants. Today, I will try to focus on the upper part of the graph, but before I do that, I will make some comment or some generalization in a sense having to do with these constructions through topological strings. So I explained yesterday this relation to knots and mentioned that these knots can be engineered in some Calabi-Yau setup where Calabi-Yau manifold is resolved conifold. So this is also briefly summarized here in particular, well, in those bars.
What means engineered? We are not engineers, so...
Yeah, I mean that to get like invariants of a knot, which are not like polynomial not invariants, like Humphrey polynomial or other classical polynomials, we have to compute expectation values of Wilson loop operators. So these are some quantum field theory operators which involve integral of a connection along some closed path, which is identified with a knot, and this is in S3. And by engineering, I mean that we, well, this is construction proposed by Witten in the 90s. You can get description in terms of this Chern-Simons theory of some topological string theory, which is in deformed conifold geometry, so T star S3. And then a knot is realized as an intersection of certain number of branes, as physicists say, they are wrapped on S3, and then there is some extra brane which is intersecting S3 along a knot. And some amplitudes of this topological string theory in this setup reproduce not invariant given just by this Wilson loop expectation values in S3 in Chern-Simons.
And this concerns only the group SUN or UN.
It is
whatever.
also for other groups. So one have to get other groups.
How you if you start with an arbitrary group, so how you produce this?
Yes. For orthogonal groups, there are some other types of branes in string theory which are called orientifold branes, and then they can be used to get invariants.
So it goes by series. Yeah, if I start with E8, so what will you do? There are many simple and semi-simple.
Well, to be honest, now I can't say. I don't remember what is
so
for
then okay.
But
it's for classical Lie groups.
Sure. So also what I just mentioned is how this knot is engineered in S3. And this string theory construction is important because then one can consider this process that I referred to as geometric transition, where T star S3 is replaced by resolved conifold. And from that viewpoint, one get this integral of Uri-Vafa invariants, which we, for example, show their integrality using this techniques of quivers. But what I want to say now is that to get these different knot invariants, we have to consider the same Calabi-Yau manifold. So after this geometric transition, this is resolved convolved. This is what you see in the storic graph in this slide. And then some, let's say, for more complicated knots, we need more complicated brane, which was encoding a knot before this geometric transition. And in this picture, we have just a toric diagram which involves so-called Haganagi-Jwaffa brane. So this is like the simplest type of brane. It encodes unknot invariants.
So I'm confused. So if you have a toric Calabi-Yau threefold, yeah, there is something called toric diagram. I understand there is a torus section. So
Yes.
you have fixed points, fixed lines, and so on.
So this is
but what is whatever Haganagi-Jwaffa branes? It's what? Toric invariant Lagrangian or what?
Yes. So this is certain Lagrangian brane, which what we see here, this is represented by this dashed line on top of the picture. And this picture shows just the projection of this Lagrangian brane on this plane, which represents the toric geometry. So there is also like torus vibration over.
So it's some piecewise linear subvariety over each one-dimensional actually. So it's a graph or whatever.
Yes.
With a torus vibration over.
And then it provides boundary condition for open surfaces that then translate to those not invariants. So what I'd like to mention now that we can do somewhat opposite process. Instead of keeping this Calabi-Yau manifold to be this resolved conifold and considering more complicated branes that represent more complicated knots, we can keep this simplest type of Haganagi-Jwaffa brane, but consider more general Calabi-Yau manifolds. And well, we also don't have the most general picture, but there is a class of manifolds which are called strip geometries. They are called so because their toric diagrams arise from triangulation of something like a strip, which is shown here. Here are two examples. So essentially, these geometries, they are toric and they do not contain compact four cycles. This is the essential feature.
Compact four cycles should correspond to closed polygons in the picture.
Yes. So we don't have closed polygons in this case. And in this case, we can also represent the amplitudes for those branes in form of this quiver generating series. So here is some general result for such a brane amplitude psi f. This f has to do.
So what it counts? Does it count what? Actually, what it represents? You should count what?
Mathematically, these are open Gromov-Witten invariants, which represent surfaces that end on this Lagrangian brane. I mean, they have boundary on this Lagrangian brane.
So whatever you call Lagrangian brane, since it's toric, it's non-compact, yeah?
Yes.
How you can count something which with a boundary on non-compact Lagrangian? You should be careful about that. Either you count in some whatever torus, it's a toric equivariant count, or you should say what are the conditions at infinity. Otherwise, there is no moduli space.
Yes, there is such an equivariant action involved
Yeah,
in.
but whether it is defined, the count is defined in terms of this torus action, or the corollary is that it's defined in a different way, but can be counted in terms of, I don't know, fixed locus action on the virtual cycle of that moduli space.
Mm,
So, I mean, did physicists ask the question, what do they count, or they just
yeah,
count?
sure. They asked, to be honest, I may not be able to express it now, but this
Because
is
it's a
also what is
nice
called.
expression, it cannot appear just
Yeah,
randomly.
sure. So in the simplest case, when the storic diagram is just one trivalent vertex, it represents C3. And in that case, this amplitude is just quantum dilogarithm.
But what does it count? What's your Lagrangian subvariety for this? It's C3, it's Mercedes, it's a very non-compact, I would say,
Yeah, sure. So
Calabi-Yau
all
manifold.
of these, yeah, so all of these are non-compact. Both
Yeah, okay.
Calabi-Yau are
Okay,
non-compact.
what Lagrangian, what's the toric shadow of the Lagrangian, which you called Aganagich-Waffa? I know Aganagich, I know Waffa, but
Uh,
what do
well,
you call Aganagich-Waffa Lagrangian? What is it?
I represent it just by the storic graph, by this dashed line, generalizing this picture from the.
But what is it? Is it any, I don't know, any line or
Yeah,
any?
this is a line in with some torus fibers
Ah,
uh,
okay.
over the line.
All right. Yeah. So then, still, how you define the count, I am not quite sure, because I remember that mathematically, even for Guri-Waffa stuff, when you have mm, just a resolved conifold and a knot, yeah. So mathematically, it's not quite trivial. It's old work by Melissa Leo and Sheldon Katz, how to define open Gromov-Witten invariants in that case. So then
So yeah,
somebody, maybe mathematicians or whoever, should take care about foundations.
that's right. I think they are understood. I may not be able to say that on top of my head now,
Yeah.
but whatever I present here generalizes the Soguri-Waffa picture, which is just for resolved conifold. So I just want to note that for this class of Calabi-Yau manifolds, we can also find corresponding quiver picture. So this amplitude I write here, this is some representation of that which can be found, for example, using topological vertex. In this expression, alpha and beta represent some Kähler parameters of this Calabi-Yau manifold. So I don't want to be too technical and go into details, but it of course depends on the scalar, like closed parameters, which are represented by these finite segments in the story graph, and also depends on this modulus of this brane, which is x. And in particular, for specific framing, this reduces just to Q-hyper geometric function. So then we find that this expression can be represented in the form of this quiver generating series with some specialization of this generating parameters xi, and which specialization involves the scalar parameters which I denote by alphas and betas in this expression. And also this amplitude is satisfies some difference equation of the sort we discussed yesterday, which in the classical limit when Q is 1 reproduces the mirror curve for this geometry. So in this picture, this node.
Sorry, Peter. Are we talking about every time about SU2 case? Because for higher ranks there should not be just one a polynomial. It's many
Well,
of.
I'm talking of not just SU2. This is like taking symmetric representations, but for arbitrary SUN.
But then there are many monodromy. I mean, it should be.
Well, I'm not considering knots anymore.
Ah,
These are not knots.
they are something which are amplitudes, and in the case of knots, it will be SU2, probably. But
In case of knots, it would be this situation Humphrey. So like having symmetric representations, so represented by Young diagram, which is just one row, but for SUN with any n, and then there would be dependence on this parameter n. So this is what happens already in Oguri-Vafa picture, like I had here. So this is resolved conifold, and this parameter n corresponds to the scalar modulus q. Q is something like exponent of n times h bar.
yeah, but geometrically, it's probably, I don't know, exponent of the area of the CP1 in the Keller structure, which actually I'm not sure anybody has written for the resolved conifold. What's a Calabi-Yau metric? I don't know.
Well, I don't know Calabi-Yau metric as
Well,
such.
if it's Calabi-Yau, then one can at least ask what for this non-compact Calabi-Yau, what can be the Keller metric.
Yes. Well, I cannot write it explicitly, but I just think that this is not SU2 situation, but
yeah, all right.
okay. And also, let me also mention that in one of the papers, we have found some explicit formulas for arbitrary quiver for so-called classical BPS numbers. So those which you obtain by resumming over all this motivic index J in omegas. And I'm not sure if they were known, for example, by mathematicians, I mean, these formulas, but...
I don't know. You mentioned last time that there are some operations on symmetric quivers which eventually reduced the story to the M-loop quivers. For M-loop quivers, it's easy to compute DT invariants.
Yes, but when we make this reduction, then it involves some non-trivial summations of this M-loop quiver. So this is still quite involved.
Okay, all right.
But for this just classical BPS number, we have some explicit algorithm which enables us to find them. And for example, here in this like bottom part now are these BPS numbers for this strip geometries. And one thing which is, for example, non-trivial, we know by this general theorem.
When you write explicit formula for numerical Domnall-Thomas invariants of what? Are you on the quiver side or it's something on the topological string side?
Well, in a sense, both. So on topological string side, there are some BPS invariants which generalize those invariants that Oguri and Vafa introduced originally. They also...
But this 1802, blah, blah, I don't know what that paper, but it's devoted to what? These explicit formulas. Formulas for quivers or for...
Yeah, I mean, on one side, from physics perspectives, we have this generalization of Oguri-Vafa invariants, which count some BPS states. But in that paper, we show that they correspond to motivic, or well, this classical limit of motivic DT invariants for quiver that encodes amplitudes for this generalized geometries I am discussing now.
Okay, so all right.
And by general quiver representation theory, we know that these omegas are integer, which is also not obvious from these expressions. So it also raised some interest in like a number theory community. For example, here is some paper by some people that you might know where they analyze that more from like number theory perspective, those integralities. So this is, of course, not very general picture, but I want to stress that we are not like bound just to resolve conifold and knots when we discuss this quivers, but they also may be introduced for more general Calabi-Yau's. And this is like the first part I wanted to present. So I'm not sure if there is an immediate question, but now I'd like to move to this upper part of this diagram I had and discuss a bit more the relations to those 4D unequal to theories. Sorry, I put on headphones because okay. So yeah, now I'd like to discuss some connections for the unequal to theories. And again, we have some like physical picture where these quivers we consider symmetric ones. They encode some 3D theory, which can be defined by considering four-dimensional theory on some space whose boundary gives the space where this 3D theory is defined. And in particular, we can relate Kontsevich-Soy-Bellman operators that arise in those for the theories, and specifically they of course appear in wall crossing identities and also in some observables that physicists called Schur indices. So we can relate this situation or in a sense represent them in terms of symmetric quivers as well. And this is a very brief summary. I'm sure this is what you know very well, of course. Jan was one of the founders of that theory, but just to summarize and introduce some basic notation, these operators, Kontsevich-Soy-Bellman operators that I'd like to discuss are expressed in terms of quantum dilogarithms, which are here in the bottom, whose arguments are elements of quantum torus algebra. And these operators in quantum torus algebra, they are can be assigned to a node of so-called BPS quiver. So this is another type of quiver, which for physicists describes BPS states in some four-dimensional theory. In this picture, maybe this is not quite standard, but for some reason we used it. By this symbol, I mean that we have two arrows just in this example. So this double arrow is like representing two arrows from left to the right. So in particular, this is not symmetric quiver, and it represents, well, in this specific case, in fact, it represents the states in SU2 Seiberg-Witten theory. So the states comes with some charges called gamma I, which can also be assigned to each nodes in that quiver, and the number of arrows in this quiver is given by what physicists call Dirac pairing. And then this Kontsevich-Soy-Bellman operator is given by the product in some specific order of quantum dilogarithm with arguments which are these elements of quantum torus algebra. So now it turns out that this can be represented like, let's say, equivalently in terms of symmetric quiver as follows. Namely, we can represent or realize this quantum torus algebra in terms of operators, this small x hat and y hat, which satisfy y relations. And then if we write each element of this quantum torus algebra xi or x gamma I as follows, like here in this middle line, introducing some Cij constants, which correspond to this Dirac pairing gamma I, gamma ij, then such operators satisfy the same algebra. And then instead of considering concept an operator, we can normal order them in a sense of putting this yi's operator to the right of the expression and then evaluating on identity. And then instead of having operator expression, we end up with the following expression, which again represents generating series for symmetric quiver with this Cij originating from this four-dimensional picture.
So Piotr, this BPS quiver with some kind of mysterious thing, is it unique for a theory?
No, it's not unique, and one can, when one changes chambers going through wall crossing, then it corresponds to mutations on that quiver. So usually when one writes BPS quiver, then one chooses some chamber where this number of BPS states is minimal and number of vertices in the quiver is also minimal. So that's, for example, in SU2 theory, we have one chamber that physicists call strongly coupled chamber, where there are just two BPS states which are represented by nodes of this quiver. And by wall crossing, we go to another chamber that what we call weakly coupled, where there is infinite number of BPS states. And of course, this is encoded in this wall crossing identity for SU2 theory.
So, but is it true that whatever you call BPS quivers, they're all mutation equivalent?
It is no, this is for some specific class of theories.
And
so,
what is this specific class of theories?
So this is class of theories which correspond to quivers of so-called finite mutation type. So,
but it can be an infinite orbit. Mutation do not have to be finite. So, but it's still whatever is BPS quiver. It's a representative of a mutation class, of a equivalence class on one orbit, or there can be many orbits of non-equivalent these BPS quivers, because you compute something in the end using BPS quiver. If there are many non-equivalent, so then the question is why your computations agree.
well, I think there is just one representative. So like in this example, like for, I'm not sure if this is the same language, but in this canonical example of SU2 cyberwitten theory, we have just these two chambers and
but it's and so then the BPS quiver is what? Is K2 quiver, Kronecker with two arrows?
In this case, this is Kronecker quiver. So in fact, what I want to discuss in what follows is just a family of Kronecker quivers.
Okay, all right.
And okay, so this is again the example when I take M Kronecker quiver, then this concept is an operator that I would construct would be just a product of two quantum logarithms which correspond to these two nodes. And now if I represent this elements of quantum torus algebra in this way, which I just mentioned, and take this normal ordering of this operator, then I find expression which encodes a quiver, which is in this case, in fact, just a symmetrization of this original BPS quiver. So for us, as I say, we have some like physical explanation where this original Kronecker quiver with this quiver matrix here represents 3D theory. And well, maybe you can treat it just as some trick of relating this concept terminal operator to symmetric quivers, but in fact, it turns out it's useful and enables us also to compute some invariants, in particular, some of these wild invariants. Where wild invariants, let me explain in a moment. are specific class of these invariants which arise in some dense families. And they are also related to certain quantum dilogarithm identities which have been like explicitly written down by Reinecke. So this is what I'd like to present now. So this identity in the frame is one of these Reinecke identities, which corresponds to M. Well, this is general form of that for M. Kronecker quiver. So on the left-hand side, we have two quantum logarithms which correspond to two nodes of this M. Kronecker quiver. And then depending on this parameter M, we have right-hand side, in general, when M is greater than 1, this is infinite product of quantum logarithms. And if M is greater than 2, then in fact, we have a dense set also of products here. And well, here are different notations. I also don't want to go too deep into all these technicalities, but again, M for M Kronecker quiver is this Dirac pairing from physics perspective. A and B, which appear in this formula, they represent multiplicities of some fundamental charges, gamma 1 and gamma 2. This sigma, which appears in the subscript, is just some operation which takes A and B, which are integers, into some other integers. Mu, in this case, there is a specific form like here, and this is the range in which this ratio of A over B appears in this part of the product. And then phi's are, again, quantum logarithms with some specific arguments. And in particular, this term here, phi with this superscript PAB, denotes the following product of this dilogarithms with this CAB in the exponent, where CAB are Donaldson-Thomas invariants for this problem. Sometimes they are denoted also by omega like this, so there are two equivalent notations. And physicists also consider some quantity which is called protected spin character, denoted by omega. So omega is related just by simple factor to this polynomial PAB, which whose coefficients are this Donaldson-Thomas invariant CAB. So the question is, what are the CAB which are encoded by this identity? And it turns out they are not known. Reinecke showed that this identity takes this specific form, but he also found some examples of this DT invariants, but not general form of them. And this is something that we hope this relation to quivers can help. We also find some examples just using this perspective of symmetric quivers.
And I have a question, because of course the general form of the wall crossing, it's the same as in our story with Maxim,
Yes.
but if I remember correctly, he used homological Hall algebra for that. Am I mistaken?
Yes, yes.
And so then, at least for the quiver K1, which is the same as quiver A2, just fully algebra SL3, there is an underlying algebraic story that the identity, this identity is 5-term identity,
yes,
for
exactly.
the quantum dialogue.
Yes,
but
yes.
that's good that you have this slide.
Yes.
So it corresponds to representations of the cohomological Hall algebra as a tensor product in two different ways. And so I'm wondering whether Reinecke had a similar, whatever, maybe you, for the previous, whether he has a similar explanation for this infinite product on the right-hand side in the previous.
Well, I'm not, well, depending what you mean by similar.
Similar means the following. If you have this black quiver, A2 quiver, all right, so then with each vertex, one can associate what probably for you it's a BPS algebra. For us, it's a cohomological whole algebra. It's a free fermion algebra. Grassmann algebra with infinitely many generators.
I think he associates it. I can't also give details now. I don't remember.
So in his paper he did it. Yeah. So he has
I,
for each
that's
root
what I recall.
for
I
for
can, yeah,
ah, it's fine if he did because I am in doubt. I mean, it's not certainly it's not easy. All right. So okay, maybe I
yeah.
should look.
So this is a special case of course, this identity where in fact instead of infinite product we have just three terms on the right-hand side, and this is also called well, pentagon relation. And then if you make this relation to symmetric quivers, which I just explained, so represent the sexes by this wide algebra, and then take this normal ordering, which produces quiver generating series, then this identity translates to this identity that I presented yesterday, which is called unlinking. So
Yeah, and so that's what I really want to understand because there are many questions related to this specific story, in particular this this unlinking, as you explained, if I remember correctly, it just invariance of certain generating function with respect to
yes,
some operator, but that's not
yes,
what I want. I want some operation on cohomological whole algebra, which makes this, which I don't know, it's not categorification yet. Categorification is a next step. It's algebraization because this quantum dialog is just characters of this free Grassmann cohomologic, this free Grassmann algebras. It's not a big deal. But what happened with the BPS algebra when you apply this red arrow?
well, yeah, this is not something I can also say now because we didn't consider that on the level of algebra. But
Because
I
it's really,
just,
it can really explain what's going on with this symmetrization. Because you know,
I
quiver
agree on this.
quiver A2, it's not symmetric at all. Then you
Of,
symmetrize it
yes.
uh, and you write down. Okay, can you just repeat in this particular story? So your generating function is what? You just write the standard generating function for whatever BPS
Yes.
invariants for this quiver. Then
On the
you
left,
rewrite it in a different way in terms of the symmetrized quiver. Yeah.
no, 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 no. I have symmetrized quiver already here.
No, you don't have it because it's not symmetric. No, it's below, but I am interested in
Below,
the black quiver.
in the
So
black quiver.
this first identity, okay,
Yes.
it can be explained
This is
entirely in terms of this black quiver, A2 quiver.
yes,
You
yes,
don't
yes.
need to double. So
Of course.
for me,
Yes,
it
yes. And
looks
this is
like you have an
operator.
alternative explanation. I would like to understand it. All right. So, and then this left-hand side, whatever, or the right-hand side, they are equal in the end, but they are equal to the generating function, certain generating function associated with this A2 quiver. Yeah.
Yes.
All right.
Well,
Good.
they are
First,
not equal, but when I make
no,
this,
they're
what
equal
I,
because they're equal among themselves. So it
if I
just
make this normal ordering, what I call. So this identity on top, this pentagon identity is like operator identity for operators. But so
okay, normal ordering for you, mathematically, you just have a non-commutative algebra, you know, cohomological whole algebra. And these are just generating series and you multiply them, that's it. Normal ordering is something
Yes, yeah.
from a different kind of different science. So then the identity can be understood without higher mathematics. It's just simple algebra. But then you say that you can reinterpret it in a different way. So in this simple example, tell how to reinterpret this identity, which I understand very well, in a different way. What should I symmetrize and what should I do? Right.
First, so the with this group is traced,
Okay,
you
you
know,
symmetrize your quiver. Good. Then what do you do next?
and then I do this unlinking operation, which I introduced
No, no, no,
yesterday,
no. I'm
which,
not asking about the identity. I'm asking about the initial generating function. This unlinking gives you the identity because I see two
yes,
vertices on one side and three on the other,
yes,
so
yes.
clearly they were. But the identity for the original A2 quiver, how it is related to anything associated with the symmetrized quiver?
Well, I'm not sure which identity you mean. I
If you
mean,
go back, you have some generating function. I do not mean the identity. I mean,
well,
whatever. Maybe you should go back even further. Whether this generating function appear for the first time. I don't
but
know.
for the symmetric quiver, is that what you
Not
mean?
for the symmetric. There is nothing symmetric in the story. Even here
Or so
on
which
this page, nothing is symmetric.
Yeah,
You
yeah, yeah,
rewrite
sure. Yes,
something
yes, yes,
for DN equal to theory, there is nothing symmetric. BPS
yes,
quiver
yes,
is not
yes. Of
symmetric, all
course.
right?
Yes, yes,
So
yes,
then
yes,
you have some expression associated with a non-symmetric quiver. Then
yes,
exactly on this slide, you rewrite it in terms of the symmetric quiver, yeah?
yes,
This, whatever you call KS
yes,
operator, you have rewritten it in terms of some symmetric quiver which was not in the story at all right?
yes, yes.
Okay, good. And so that's a part which I do not understand. Can you, on the physics level, can you explain this in terms of a BPS algebra of the original quiver? What do I do?
Mm, well, this amounts to representing this elements of quantum torus algebra in this way. I'm not sure if this is the question.
Mm, I don't know. I mean, yeah, but that's it's something indeed, some formal thing, but uh, you see, BPS algebra, you have some physics understanding of what is it. At least your co-authors, two of your co-authors, Tosic and Gukov, should have some understanding of it. And so you have some identity. Let me tell you, this operator can be interpreted as an element of BPS algebra, of your BPS quiver. You don't have to symmetrize it.
Yes,
No,
yes, yes.
this operator, all right? You can realize it in the representation and operator form, blah, 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 but you don't have to. All right, and then you rewrite it in terms of a different quiver. And what it means, I don't know, physically or...
Well, okay, so we have like a physics picture where mm, we relate data that defines this 4D Fiore to data that defines 3D Fiore. And 3D Fiore, as I mentioned, appears on the boundary of 4D Fiore. But the way we realize it is that to define 4D Fiore, we can also consider Seiberg-Witten curve. And
Yeah.
then, in particular, BPS states correspond to, or at some chamber in which we are corresponds to some triangulation of the Seiberg-Witten curve. And so this BPS quiver for us also encodes some data related to this triangulation. And on the other hand, the three-dimensional theory that we get has ingredients which correspond to certain tetrahedra which build some three-dimensional manifold. And such three-dimensional manifold whose boundary is this Riemann surface which was defining 4D theory.
And triangulations correspond to triangles on this ideal triangulation by tetrahedra.
Yes, and then symmetric quiver encodes the structure of this tetrahedra. So in that sense, that's the relation between this 4D and 3D.
Yeah, because it's something which can be useful, at least it looks for me, it can be useful even mathematically.
Yeah, I very much hope that could be also translated to
all right,
proper mathematical language. But
okay, go ahead. Yeah, and sorry for the interruption. Yeah.
Okay, so this was this one example. Well, and then we have some other examples. So when you have this Kronecker quiver with two arrows, which again is example of this so-called SU2 Seiberg-Witten theory, then this identity, well, this is also one of the standard wall crossing identities. So this is one of these cases that Reinecke has, which again has two logarithms on the left-hand side and then infinite number of quantum dialogues on the right-hand side, but at least this is countable.
Well, it's always countable. I don't want to kind of disappoint you, but from general theory developed by Maxim and myself, you always have no more than countable. Yeah, so it's not
it's not. I meant that for m greater than 2, we get dense set, and then this
there is some
BPS
wild
invariant.
chamber, everywhere dense,
So that's what I had in mind. This is not dense, but and we can then also do similar exercise like for the Saito quiver I had before. So in terms of symmetric quiver, the left-hand side corresponds to the symmetrized version of this Kronecker quiver, and on the right-hand side we get some, again, symmetric quiver. This is just given schematically here. So those numbers represent numbers of pairs of arrows or loops, and again, it has this property that generating series preserved. So in a sense, this is some generalization of this unlinking operation to the case of this quiver with two arrows. And then we can do also similar exercise for those wild cases when m is greater than 2. And we can use this formalism of symmetric quivers to determine those wild DT invariants. So we do this in two steps. First of all, we find this infinite quiver which arises from this wall crossing identity and its symmetric version. And then we use this operation of diagonalization, which enables us to relate, to express everything in terms of invariance of LMOV quivers. And this is the identity, it is, it is schematic, but essentially identity which relates this wide DT invariants which are here. So for us, they come from this 4D theory. They are related to invariants of symmetrized Kronecker quiver in this case, and invariants of those K-loop quivers. Here K can be arbitrary because M is number of arrows, so M is fixed here, so I call it K-loop in that case. And then in this operation of unlinking and then the diagonalization, we get some series of, well, we create extra nodes of a quiver. So this is represented by this summation, like schematically, we call it a trees of unlinkings where we get more and more nodes in a quiver, but we get this type of identity which relates this motivic invariance of 3D quivers to this 4D invariance. And using that, we can find some examples explicitly of this wild invariance. So this is at least some practical application and advantage of this viewpoint. So, well, this is example of also those infinite quivers that correspond to M Kronecker quiver, and they are quite involved, as you may just imagine from this picture, but it can be made at least work in practical way to find some of this wild invariants. So that's one advantage that we find of this symmetric quiver, and I will briefly mention another one which has to do with some other physical quantity which is called superconformal index, which is also some observable that characterizes those for the n equal to Fioris at so-called superconformal point. For physicists, this is defined by some trace over Hilbert space of states in S3. And so there is some other definition of this quantity, which I also don't want to present in detail, but there are statements that this should be also possible to represent by Ks operator, which involves all BPS and BPS and anti-BPS states, because this should be chamber independent. So one should be able to represent this superconformal index by something that some quantity that does not depend on a chamber.
I'm confused. You have a product, but if you have kind of a chamber and anti-chamber, so you should have products which are infinite in both directions. It's like product over all integers.
Well, here I mean finite products. So if I had
finite. All right. Yeah.
Like in this example fine. Of SU2 Fiore, previously I had product which involved just two logarithms corresponding to this BPS state.
Yeah, on the left-hand side, yes, but on the right-hand side.
Yeah, but now I am like just on the left-hand side. When it is finite,
okay.
I include those partners.
Okay.
So there is a statement that this quantity, this index, is given by the following expression. There is some factor involving Q-Poch hammer, which corresponds to what physicists call vector multiplets, and then some trace of this Ks operator in this case. And it was evaluated in particular in this paper by Cordova and Shaw already like 10 years ago in the following form. And then in this paper we had recently, we showed that this can be also rewritten in a way which involves quiver generating series for certain symmetric quiver, which is shown in this picture. And again, this symmetric quiver has some part which involves symmetrization of this original BPS quiver. But because we also include this anti-BPS states, we have twice as more nodes. So those black ones are a consequence of having this anti-BPS states. And this can be, well, again, this exercise can be repeated for other cases. So, for example, for our Douglas Fiore, for this, which corresponds to the A2 quiver, we can also do that, or in fact, for any Arger's Douglas Fiore with this index to n. And furthermore, it is also shown, well, it was conjectured earlier and also shown in this paper by Cordova and Shaw that these indices which appear here, in some cases, and specifically for Arger's Douglas Fiores, they must have modular character, and for that reason they turn out to be equal to certain characters of vertex operator algebras. And in particular,
this modularity, they prove it just by brute force, or?
well, on one hand by brute force, but there are also physical arguments that there should be modular invariants based on engineering these theories also in some brain setup in string theory. So in particular for this A to N argument Laplace theories, the Schur index takes form of so-called vacuum character of this 2, 2n plus 3 Virasoro minimal model. And this also gives us new ways to understand and write expressions for these characters. So for example, here in this first line, this is some classical expression for these characters. This is for n equal 1. So this is 2,5 Virasoro minimal model. And this was known for at least from the 80s or so. But now we know that this is reproduced by this index, which we can also write in this form of quiver generating series for, well, for A2 Fiore, this is for this quiver which I had in this picture. So somehow this specific symmetric quiver, it knows something about this character of 2,5 Virasoro minimal model. So this is one manifestation of this relation to two-dimensional theories. Okay, so this is what I wanted to say about these 40 theories, and well, my time is running out, so I maybe will not present details, but let me just say in 2 sentences that in some specific cases we have also some combinatorial models which reproduce the counting of this Donaldson-Thomas invariants. And these counting models are some combinatorial models of lattice paths of the type that you see here. So the lattice paths that we count are constrained by some line of some fixed slope in this picture, and then we count all lines which are made of steps to the right or to the top. And yeah, I don't want to take too much time, but this is quite simple setup. In fact, so this type of lattice models, they correspond to quivers that arise for torus nodes, arbitrary torus nodes of type R, S, like in this statement here below this expression. So in particular, the slope of this line is R over S, where R and S corresponds to the type of the torus node. So it has, again, more to do with this relation to nodes and this nodes quivers correspondence. But I very much hope that it would also be interesting to understand, like, more mathematically why these specific combinatorial models arise. And well, this is example of a quiver that we get for trefoil node in this case, and then these paths for trefoil node we consider paths under the line of a slope 2/3, and their counting in some way reproduces this invariants of this node and also corresponding DT invariants. So we have some explicit expressions as well for other nodes. And also we have generalization of that which has to do with Schroeder paths. So Schroeder paths are paths which, apart from the step to the right and to the top, also involve a step which is diagonal one. So there are some examples of these Schroeder paths, and this type of combinatorial models again encode some invariants of quivers corresponding to torus nodes. Okay, and specifically there is some subset of fundamental paths which are in one-to-one correspondence with the nodes of a quiver. So if there is some proper mathematical formulation, then these elementary paths should somehow be seen as corresponding to the nodes. And on the other hand, in this knot theory picture, these paths also represent correspond to generators of Humphrey homology of a given knot. So, okay, so I think this is what was my plan to preserve. As you see, there are many things which are properly not, hopefully not yet mathematically defined, but we see that this symmetric quivers may be related to these different contexts, and well, we hope this is not accidental. We have these physical explanations, which I was not presenting in too much detail, but like this relation between, for example, triangulation of this cycle-Wheaton curve and this tetrahedra, which encodes relation between 4D and 3D theories, hopefully gives some explanation why these quivers play such a role. So maybe I can stop at this moment.
Thank you very much. Are there any questions? Yeah. So for you, when you say, you gave many kind of examples of concrete theories with and BPS quivers corresponding to them, so your generating functions kind of came from the nature. But when you explain your this symmetrization procedure, you started with an arbitrary quiver. So it doesn't have to be a BPS quiver. What is BPS about it?
Well, it does not have to be BPS. The reason that we consider this BPS quiver is that in that case we know explicit form of this wall crossing identities, and
No,
we wanted
the wall crossing identities, we know, I mean, not in explicit, but in some abstract form, we know for any quiver. You know, it's if you need to compute something, then you're right. You need some this indices, blah blah blah. But if you want to show that something is equal to something else, then you don't need
yes.
details. So then basically you start with an arbitrary quiver, at least what it looks, how it looks for me. And you maybe, I don't know, maybe loop free, that's I'm not sure. And then you consider the character of cohomological whole algebra. That's what you call this
Yes.
KS operator, whatever. And then you rewrite this thing in terms of symmetrization of this quiver. It
That's right.
should be general statement. Yeah, all right. So
Yeah, I think the statement is general. What was maybe more specific was this wall crossing identity, which relates it to some other quiver, and this is where we
no. Well,
focus.
crossing identities, it's just the fact that actually it's okay. So actually it might be a good point. So if you do a mutation, all right, the number of vertices do not change. You get another quiver with the same number of vertices. And then you are in a different chamber, you can define the cohomological whole algebra. At the level of characters, uh, we know what's going on. It's written in our paper with Maxim. So then you have control on these generating functions. But what happened with symmetrization? If you symmetrized in one chamber, then did the mutation and
No,
symmetrized in it.
but I didn't make mutation here. I meant this
I
identity
do.
that
I do.
Reinecke. Okay.
No, Reinecke, I mean, I don't understand what actually Reinecke have done except of explicit numbers.
Okay.
What I'm
But we didn't
telling you
consider
that
mutation. Yeah.
mutations, again, that's all story in our paper was 16 or whatever, 15 years old. It's explained what's going on with character of the cohomological whole algebra when you do a mutation. It's an interesting story, but it's done. But if you symmetrize the generating function in one chamber and did a
Oh,
mutation and, you get a different quiver. So when you symmetrize in a different chamber, it should be a different double quiver.
Yeah. I suppose, it might be again related to this unlinking
Yeah, that's
operation.
actually that's my question, whether these
Yes.
quivers can be symmetrization. Okay, good.
Yes.
This is
So
where,
in this paper
okay.
from April, which is here, we also, at least for some class of
Uh-huh.
examples,
Yeah.
we analyze this mutation, and then what do they correspond in the language of the unlinkings. Yeah.
Okay, great. So let's explain a little bit about this unlinking that just comes from mutation and symmetrization. And another question is that in general, even I believe for d n equal 2, you have not only a quiver, but a quiver with a potential. Yeah, there is some function. All right.
Yes. So
Is
this
there
I
an
cannot
analog of
tell.
symmetrization of that story?
I don't know at this moment. Yeah, I can say.
Yeah. So it's interesting. I do not understand your symmetrization, so you're right. Okay, more questions?
Yes, I do have a few questions. So still on
You
this
have had the
conservative
chance to
solvable.
answer them, to ask
Huh?
them.
Can you hear me?
Yeah, I do.
Okay, so yeah, so this phi x, which is supposed to be counting some things, what does it count for? This looks like a single vertex, a quiver with one single vertex in
Well,
the in the conservative Solomon operator definition.
uh,
That is
quiver
in
with just
slide.
one vertex. Yeah, so in that case, this is given by. Sorry, how can I go back? For quiver with just one vertex,
Go
we will
further.
get.
Yeah, just one single vertex, no arrows at all.
Yeah. So then we get quantum dilogarithm, which counts Young
And that the
diagrams.
phi q is the phi. It's exactly the initial phi x.
Yeah. I mean,
Go
it
back.
counts Young diagrams. I'm not sure if this is what you're asking about,
Yeah.
but it counts Young diagrams. Like here, if I would just
Uh,
reduce to single vertex,
mhm.
then this expression, it reduces just to all these factors with alpha, beta disappear. I had just this part with inverse cube of Hammer, which you can rewrite as, it's like, it gives generating series of partitions.
Actually, what I'm asking is much simpler than this. Is the in the conservative Solomon operator in the 4D n equals 2 theories slide.
Oh, you mean what would
Yeah,
be
that's some.
if I would have
Yes, here. Oh, yeah.
just a single
Just,
node?
go back. Probably.
Well, it would be
Oh, yes, in the
similar.
bottom. Yes, it is in the bottom. Yeah.
It's in the bottom, so I would have just single phi, which is here on the right-hand side, and this is what I would have in this
So
symmetry.
for each k fixed, what is the coefficient counting? If a q is the number of elements in over a finite field.
Mm. Well, all I can say at this moment is that, again, in this case, this psi in the bottom is generating series for partitions. But how to relate it to what you're asking, maybe I can't say immediately.
I see. So when you define this PQ on the left-hand side here, you have this x1 up to m, and you order the vertices 1 up to m in such a way.
Yes.
And if I have a quiver, for example, for the blue quiver, and do you want the arrows to be pointing from
Here
smaller
we choose
to larger ones?
here we choose specific ordering. Well, in physics language, this has to do with those phases of central charge, which
and at least from the example, the chronicle quiver or the A1 quiver notes that the arrow is always pointing from small x to the larger from the small number. Okay. Now for the A2, the PBS quiver, that one I can get a feeling. Yes, perfect. Thank you. Left-hand side, that's a symmetrization of the A2 quiver, but the right-hand side, and this two quiver in terms of quiver representation, they have the same number of, there is a correspondence of indecomposable representations. And
you mean this quiver on the right?
yeah,
That's
basically, I mean, giving a
representation.
quiver of representation on the left-hand side and applying this is a very elementary algebra called the Fitting's lemma. One can decompose that quiver as a direct sum of three parts. One part completely concentrated on one vertex on the left, another one concentrated on vertex on the right, and the middle part consists of the arrows go back and forth, and both side arrows are all isomorphisms. And that is giving the representation of the all the composition is nilpotent. So that is giving the loop in the middle. So I was wondering in the canonical quiver case, what you have a picture for the symmetrization. For the canonical quiver, that means m equals 2 case. What does that arrow really?
This one?
Yeah.
Well, we know this also this counterpart of symmetric quiver, but now it has infinite size and.
Yes, yeah. In the middle, that's in terms of quiver representation. Those are mostly corresponding to the called the regular representations, and that involving the dimension vector. On the two vertices, you have the equal dimension, and which corresponding to in terms of roots corresponding to imaginary roots, and both left and right arrows corresponding to real roots.
You have real roots on the right-hand side as well.
Yes. Yeah, any cosmology algebra will have real roots, but now will have way more imaginary roots. That's why the middle is getting very complicated.
Yes.
Mm-hmm.
So
because the wall crossing formula is kind of for me, it's in terms of PBW basis. If you write PBW basis, you have to fix the specific order of the positive roots. If you multiply two in different orders, you will express back. And that's my understanding of the wall crossing formula. And this is the one. You can see the left-hand side in the wrong order. If you express
it's a very simplistic understanding of wall crossing formula, I would say.
Yeah, this is an algebraic way to understand what that means.
No, it's not an algebraic. It's a very simplistic way to understand, because algebraic way to understand it, it's to introduce a stability conditions and to look for cohomological whole algebra associated with every positive root.
Mm-hmm.
So then you have to...
Once you have every positive root, but in order to write down the PBW basis, one has to choose...
if you want
order.
to...
If we choose different orders, the basis expression will be very
that's
different.
what I'm saying you. It's not about PBW basis. It's about something different.
Mm-hmm.
All right.
And here the stability condition gives...
it's not obvious even that it exists.
It's giving a specific order for writing the PBW basis.
It's not about PBW basis. It's what we, well, you can call it in this way. It depends on what do you call it, PBW basis.
Or PBW basis in the quantum group, if you fix the order for the positive roots, so the entire algebra, and that is given by all these each individual factor phi's are the monomials, but this time the monomial is having it's an infinite sum or with coefficients of Q involved.
Yeah, so that's it's not what's happening here. Okay,
that's my question.
Piotr, I have kind of just question to you as a physicist. So this symmetrization in terms of the BPS algebra, do you have an idea what's going on?
Probably not the one that you would be happy with. As I said, one explanation that we have has to do with this relation between triangulation of the Seiberg-Witten curve and tetrahedra, which give 3D theory, but it's not.
But it's not about BPS algebra.
Yes, yeah. So I can't say about BPS algebra, but I hope this is at least interesting question that can motivate someone to think.
Yeah. Okay. All right. Well, thank you very much indeed.
Yeah, can I ask you a quick question?
Okay, this is it. You can email Zhongzhu with kind of educational questions. You can email.
Sure.
All right. So this is it for today. And actually, this is it for the M seminar in this semester. So thank you, Piotr, for your lecture series, and thanks for everyone for coming, and see you in the next semester.